Okay, so in these last two lectures, we'll talk about the fundamental principles behind the design of a quantum computer. So here are the questions that we'll ask. So how do you design physical qubits? And what we want to do is we want to be able to initialize. So we want to be able to initialize a qubit into the state 0. We want to be able to manipulate these qubits by applying quantum gates. And we want to be able to measure these qubits. Okay, now, of course, the state of a qubit is a vector, a unit vector in a two-dimensional complex vector space. So when we say these are physical qubits, what we mean is that these states 0 and 1, these are eigenstates of this physical system. And then when we say we want to be able to apply gates, what we are saying is we want to be able to apply some unitary transformation to the qubit. And the way we'll do this is by applying a Hamiltonian. And what we'll do is, when we want to apply this gate, we'll switch on this Hamiltonian for some period of time t. And then this gate, the unitary transformation, is just given by e to the I ht over h bar. Okay, so this is what we want to be able to do. Now, there are many systems for implementing qubits that people have considered, including atomic qubits, photons, spins. This is the system that we'll be looking at. Also composite systems like quantum dots or even superconducting loops. People have spent a lot of time thinking about these quantum systems. There are probably hundreds of experimentalists around the world who are working very hard on trying to implement quantum computation using these kinds of systems. It's a very hard problem. Of course, what we'll talk about in these two lectures is just the basic principles. How you would manipulate, initialize, measure qubits. Now, some of you would want to know much more, and you'd also probably want to know the state of the art in these various systems. I can certainly give you pointers to these things, and you can look up articles and papers about these various systems. Certainly, understanding the basic principles will help you, appreciate those articles in a much deeper way. Okay, so let me say a little bit about the spin. So, elementary particles like electrons and protons carry an intrinsic angular momentum, which is called spin. And when the particle is charged like an electron, there's also an associated intrinsic magnetic moment. So an electron acts like a little magnet. And in fact, this magnetic moment or this angular momentum, these are quantized. So the spin can point either up or down. It's quantized into these states. And so it's a qubit. It can be these are basis states, spin up, which we can think of as 0, and spin down, which we can think of as 1. And then in general, the state of the spin of the system is, or the spin degree of freedom, is some superposition of spin up and spin down. But where does all this come from? Well, one way that you get a magnetic moment is from a spinning charge. So you might have a loop of current, and as associated with this loop of current is some magnetic moment mu. So if you have a charge q that's moving in a circle, then it has an associated magnetic moment in the orthogonal direction. So just thinking very naively and classically, you might imagine that your electron is like a sphere which is sort of rotating about an axis. And then, of course, since it has a charge, the charge moves around in a circle, and that gives rise to a magnetic moment. Okay, but of course the electron is not a sphere, and it's not actually rotating. So the intrinsic angular momentum is just some quantized quantity associated with the electron. And of course, it's expressed as a qubit. So the spin of the electron is sitting as a vector in this two-dimensional complex vector space, in this Hilbert space. But still, we want to understand what happens if we switch on an external magnetic field B. We want to understand how it affects the spin of the electron, how this little magnet interacts with this external magnetic field. And so in order to do this, we have to understand how to locate the spin of the electron in three-dimensional space, where this external magnetic field is sitting and pointing. How do we relate this two-dimensional complex vector, the state of this spin, to real space? Well, we'll see this in these next few videos in this lecture.